Welcome to Mathematical Practice 2, Reason Abstractly and Quantitatively. Well, in light of Mathematical Practice 2, we have the following 3 goals for this learning session. Goal number 1, to understand the relationship between quantitative reasoning and abstract reasoning. Word problems have abstract reasoning. They have words, which are abstract, and those words represent numbers. So being able to go from the words in a word problem to the quantitative numbers that those words represent, and vice versa. Being able to go from numbers to words. So words to numbers, numbers to words. Goal number 2 is that both we and our students would develop a strong number sense, that we would understand numbers. We'd understand what numbers represent, the magnitude of numbers, the relationship of numbers one to another, and that we'd understand how numbers work in problem solving. The third goal is to develop a chain of reasoning, that we would have a process that we could go through, a chain of reasoning that makes sense, that we start with the abstract numbers and words in a word problem. We would be able to represent those using quantitative or number representations, or maybe even other tools or drawings or things that would be able to help us to understand what the word problem is saying. And then also to understand how we would solve that word problem. And then the final link in the chain goes back to the beginning of the chain, where we look at how we solve the problem and see, does this make sense in light of the word problem itself? Let's go. This is an example of a poster that you might use in your classroom to help students understand what is expected of them. According to Mathematical Practice 2, I can use numbers and words to help me make sense of problems. I can go from numbers to words. For example, I can go from 2 plus 3 equals 5 to I have 2 yellow flowers and 3 red flowers. How many flowers do I have? Or I can go from words to numbers. For example, we can use numbers to represent the words and understandings in a word problem situation. Here, for example, the words I have 2 yellow flowers and 3 red flowers. How many flowers do I have? Can be represented using numbers and symbols. 2 to represent the yellow flowers, plus, because I want to know how many I have when I count them together. Plus doesn't always mean that, but in this situation it does. 3, because I have 3 red flowers, equal, how many do I have if I put them together? Again, equal doesn't always represent that. 5, the amount I have when I count the yellow and the red flowers together as one group of flowers. You may find it helpful to display just such a chart in your classroom. In the reference section in the slide below, I list the resource or the source for this chart and for other mathematical practice charts that you may find helpful. As well, you will find a set of these posters in the group attachments for both the mathematical practice and this current lesson. Comprehension. Word problems don't just jump out at us and say, you need to subtract here, or you need to measure using a ruler. This requires reasoning from the abstract to quantitative, and from abstract words to math tools. Let's make a comparison between comprehension in reading and comprehension in math. Think for a minute. Think about teaching reading. How do you guide students to understand, to comprehend what they're reading? Pause to consider this question and to think about how reading comprehension might relate to math comprehension. Word problem comprehension. Just as books need comprehension, word problems need comprehension. In all comprehension, whether it's reading, listening, or math, learners need to take what is given and use that to reason through to understanding. When reading a book for comprehension, we teach students to look for clues in both the words and the pictures. We teach students to use what is given to compile evidence or reasons to determine what the passage means. So too for math comprehension. When reading a word problem for comprehension, we teach students to interpret words and numbers. Just as words and pictures work together to establish meaning when reading, words and numbers work together to establish meaning in word problems. Numbers represent situations. In our lives, we interpret meaning all the time using quantitative reasoning. Think about it. We analyze advertisements for value. We look at flyers and sold bargains. We judge the accuracy of someone else's computation and our own, especially when we do things like splitting the bill for lunch, when paying with one credit card to get a special 2-for-1 deal. We use numbers when we make financial decisions. If I buy a ticket to the concert, will I have enough money for the course books, the textbooks I need for my courses? We use numbers when we figure out how much of each type of food to purchase for a party. Let's see, approximately how many people are coming, how many are guys, who usually eat more, how many are girls, which are the favorite snacks, and how much do they cost? How much cheaper will it be if I make the chocolate chip cookies instead of buying them at the bakery? We use numbers to decide how much each meal will cost. How much is the appetizer? A main dish? Should I buy a drink? Dessert? How much tax do I need to add? How much should I tip the server? In other words, we use reasoning, abstract reasoning, all the time, and quantitative reasoning. We change real situations into numbers all the time. Every day, or almost every day, we go from abstract situations to numerical solutions. Almost every day, we solve real-world problems using quantitative reasoning. The second goal for mathematical practice 2 is that students would develop a strong number sense. In other words, an awareness of what numbers are, how numbers relate to one another, their magnitude, what they mean in problem situations. Mathematical practice 2 expects children to learn to use abstractions such as numbers, symbols, drawings, concrete materials, and diagrams to express meaning. Numbers by themselves are void of meaning. That's important. It's only when they represent a situation, when they stand for something else, that they mean something. For example, consider the number 8. What does 8 mean? Take a few seconds to think about this before moving on to the next slide. Here are a few contexts where the number 8 is used. In each, the meaning represented by the number 8 is different, depending on the context. For example, the number 8 might represent the name of something, like the name of a road. It might represent a figure, the figure 8. If you're a figure skater, you might be thinking of the figure 8 as you cut the ice with your skates. The number 8 can identify a baseball player on a particular team to make it easy to find that player on the base field. 8 can represent the grade you're in at school. It can be a part or the whole of a phone number. 8 can be the number of a pool ball in a set of pool balls. 8, the 8th in a sequence of birthdays. 8 can represent a type of knot. The context is everything. Without a context, numbers are meaningless. They're as meaningless as a blank piece of paper. In conjunction with mathematical practice 2, mathematically proficient students are able to represent quantities in various ways, using words, numbers, pictures, etc. They're able to connect numbers with words and words with numbers. They can represent a context using numbers, symbols, diagrams, concrete manipulatives, math sentences. Refer back to the problem's context when needed. They can understand and evaluate the answer. We will discuss each of these in more detail, slides to follow. Before, during, after. Here's another of the mathematical practice posters that you may want to display in your classroom. When given a problem, I can make a plan from what I know, a plan for what to do in the midst of problem solving, and what to do when I think I've found a solution. Before I can think about the problem, I can make a plan. I don't give up. I consistently ask, is what I'm doing making sense? After, I check my work. Is there another way to solve the problem? Make a plan. The first step in any plan is to get an understanding of the situation. When we get off a train, we look around. Where am I? Where are things found? The same thing if we're solving a problem. If the problem is a word problem, we'll read the problem for comprehension. And as we read, we make a picture in our head of what's happening in the problem. We're interested in increasing our brain activity, as we spoke about in another lesson, of increasing the electrical synapses between the neurons and building new neurons. Visualization will cause an interplay between the external and the internal representations, and as a result, visualization sparks brain activity. Visualizing helps us to step into a problem, to get started, to picture and comprehend what the problem is about. Visualization gives students space to go deeply into the situation, looking for clarification to help develop a picture in their heads. Visualization helps us to consider, move around in our heads, and model visually what we plan to do next. Visualization is a skill that develops with practice. Let's see how your visualization is. Visualize that you have a stack of 10 cards in your hand. The cards are in order from 1 to 10, with 1 on the top, 10 on the bottom. Imagine you deal out the cards. 1 out, 1 at the bottom. 1 out, 1 at the bottom. 1 out, 1 at the bottom, and so on until you're left with only 1 card in your hand. What is that 1 card? Check out your visualization by doing the process using an actual deck of cards. Think about this before you move on to the next slide. Were you able to visualize that 1 remaining card? The ability to visualize is important for spatial sense. Don't worry if you were not able to visualize this problem. The ability to visualize is developmental. It develops as we practice. We don't get any better at visualizing by getting older. We and our students need to practice visualizing to get better at it. Here's a visualization problem you might give your students. Consistent with pre-kindergarten to grade 2 and consistent with mathematical practice 2, put an emphasis on how many, on numerical reading. Looking at the diagram on the left, you might ask, how many cubes will it take to make this stack of cubes? Why do you think this? Looking at the diagram on the right, you might ask, how many cubes will it take to make this stack of cubes? Why do you think this? In this example, it's not possible to see under the cubes on top. We have to visualize the cubes that we don't see. By looking at the we do see, and then visualize what might be under the cubes we do see. Visualizing builds students' ability to see or describe the structure of a problem. Visualization helps to build quantitative reasoning, the ability to represent abstract situations into numbers and numbers into words and situations. Visualizing helps us to connect with what we know that may not appear in the words or the numbers that we're given. Okay, we are moving on to our third goal for this session, which is to build a chain of reasoning. Now, in that chain, we will pull in number sense and making connections between abstract and quantitative. So the first step in that chain is to make a plan. To begin to make a plan, we read the problem for comprehension and advise that meaning. We ask of the problem, what do we know? Noticing words and numbers in the problem. Consider the picture on the left of a part of a problem that preschool students are to solve. We might ask questions such as, how many bunnies do you see? Why do you think that? How many bunnies are facing right? How many are facing left? Why do you think that? We might call on students to tell a story and ask a question about the bunnies in the drawing. In other words, to make up a story problem that others will solve by using what's shown in the picture, going from quantitative to abstract reasoning. Even before they can read the words, students can count using pictures to help them comprehend what is known. Early geometry problems give known facts that we are to develop to help solve a problem. The geometry problem in the middle asks, which one of these is the same? Geometry is built on students' understanding of attributes. According to the CCSSM, recognition of attributes begins in pre-kindergarten, where children learn to analyze, compare, and describe similarities and differences in color, size, shape, and position. What's next to, on top of, under, etc. Building on what pre-K students learned about attributes, kindergarten students learn about 2D and 3D shapes, and they analyze and compare shapes using the attributes of the parts of their shapes. For example, sides, which are part of the whole, right? Vertices and corners, edges and points. The geometry question in the middle of the slide would be a kindergarten level geometry problem. To the what do we know question, students learn to analyze and describe shapes in terms of number of sides, number of corners and vertices, numbers of edges. If students are not forthcoming with noticing these attributes, we might ask, besides the color, what do you notice about each shape? How does each shape differ from the other? How would you describe these shapes using numbers? For example, how many points in the star? Does a star have any sides? Or if necessary, how many sides in a square? How many points in that star? Do other shapes have points? Why do you think this? In other words, we focus students' attention to classifying part to whole attributes using quantity, number. Looking at the frog problem on the right, what do we know requires analyzing the problem, comprehending the meaning of the words, and noticing number words like 5 and 2. So in the beginning of our chain of reasoning, we ask, what does the problem tell me? Besides, what does the problem tell me? The next part of the plan is to ask ourselves, what else do I know? What do I know that the problem does not tell me, but that I need to know to solve the problem? The answers to this question depend on the grade level. For example, what else do pre-kindergarten students need to know? That is, when I count, each object receives one and only one number. So when they're counting, if they need to know how many, they need to know that the sequence is 1, 2, 3, 4. They need to know that each object receives only one number and that the last number they counted is how many. Pre-kindergarten students may need to know this to solve a problem, even though this information is assumed and not actually given in the problem. When the problem says to measure, kindergarten students may ask, what else do I know? And they will know that weight and length are two different attributes and that different tools are used to measure them in relation to those attributes. How much of what else do I know is rooted in what students learned the year before, the prior grade standards? For example, when measuring with chain lengths, the student should know that I need a tool in which to measure, may need to know to connect links, and connecting blocks are the tools used to measure. Though it isn't given in the problem, the what else that students need to know is that one block represents one unit, and that I need to line these units, these links, or these blocks up right against what I'm measuring and count how many I have. What else do I know may require knowing which operations represent different situations. For example, if a problem gives that Joe has 9 balloons and Alice has 2 balloons, what else the child needs to know is which operation, addition or subtraction, would they need to use to represent this type of situation. The important point here is that students realize that some of the information they need to solve the problem is in their own heads, and it's up to them to figure out which information the problem requires. The fourth step in our plan is to decide on the best way to tell the story in the problem. Having visualized the situation, students will have laid the foundation for this step. Students decide if they want to draw a sketch, act it out, use concrete objects, use their fingers, or some other way to represent what they're thinking and to extend what they're visualizing. We'll go into more detail on this part of the plan when we study Math Practice 4, which is Model with Mathematics. Okay, now in the plan, we're up to step 5. Answer the question found in the problem. Try out the plan. Keep checking back with the problem situation to make sure our progress is making sense. And don't give up. During the implementation of the plan, students may begin to struggle and may need to be reminded of how important it is to think hard, to make mistakes, and struggle. As the teacher in one of the videos that you watched said to her class, "Today we will work harder to get smarter." In the midst of problem solving is where we assure students that challenges and struggles and not knowing immediately is normal, is necessary. To help students take charge of their own learning, we can ask them, "What should you do when you get stuck?" and have them become familiar with using these strategies. In the midst of problem solving is where we assure students that challenges and struggles and not knowing immediately is normal and necessary. The ultimate goal is that students would take charge of their own learning, because it's only then that they're going to be able to transfer what they learn in the classroom into their lives. To help students take charge of their own learning, ask, "What should you do when you get stuck?" And make the classroom a place where persevering, rethinking, and struggle becomes familiar and comfortable. When students struggle and we wait, we let students know that we notice and value their thinking. We might let students know this by saying something like, "From what you're saying, I can see the wheels spinning in your thinking." That's from one of the videos we watched. We might ask students how they're feeling in the midst of their struggles. And if they say, "Good," we might ask, like the teacher in the video did, "Why are you feeling good even though you have not found the answer?" And then we celebrate and congratulate students when they say, "I feel good because I'm working really hard." When you have to stop their progress due to time, say something like, "Friends, I'm going to have to stop you. We ran out of time and you were doing so much thinking." As on the video, give students time to share at the end of a problem-solving session. If we emphasize thinking, students may share, as the child on the video shared, "Even if we didn't get the answer, we were happy because we were doing so much thinking. We didn't quit. We were happy because we were growing our brain." Like the teacher on the video, let's end our problem-solving session with a positive mantra. "I'm taking charge of my own learning." The last step in the plan is to make a plan what to do when we have figured out what the answer is. Having planned for problem solving, having worked through to a solution, the next step is to check back with the problem to see if the answer makes sense. During this step, students again share their thinking and express why they think their answer either does or does not make sense. If the answer does not make sense, they start the plan over again from the beginning. The target is that students will have taken charge of their own learning and that they would feel happy and comfortable knowing that they're growing their brains and getting smarter through their struggle. This disposition will help them to view planning again from the beginning as the natural, productive way to approach problem solving. So, to review, in building a chain of reasoning, we make a plan for thinking quantitatively. We analyze the problem situation and context, read the problem for meaning, and visualize that meaning. We ask of the problem, what do we know? What is this problem telling us? Noticing numbers and words in the problem. We ask ourselves, What else do I know? What do I know about this situation that the problem does not tell me, but that I need to know to solve the problem? Decide on the best way to tell the story in the problem. For example, draw a simple sketch, act it out, use concrete materials, tell the story this way. And then check work along the way. We can ask, is my plan and strategy making sense? Pause at points to go back and forth from the problem situation to the solving of that situation, asking ourselves, does this make sense? Checking numbers and representations and the problem context to be sure that these agree and make sense. And then the final step, after problem solving, answer the question posed by the problem. Check back with the problem to make sure the answer makes sense. Check to ensure the answer fits the original problem situation. And if the answer does not make sense, start the plan over again. As Thomas Edison would say, this time with the added benefit of having learned what doesn't work. The chain of reasoning. Learning is a cyclical process, an ongoing process of getting smarter and smarter by making a plan, carrying out that plan, checking for sense making along the way, coming up with a possible solution, and then checking that answer to make sure it makes sense. And when it doesn't make sense, make another plan, this time with the added benefit of what we learned in our prior attempts. To give evidence of what you learned in this lesson, and to better make this learning permanent, complete MAP2-3, Reason Abstractly and Quantitatively. For this transfer of learning, you will videotape small group problem solving. This will be similar to the videos that you filmed when you were preparing to take the EdTPA. You will pose a challenging problem, allow students space and time to work through that problem. As they are working, you will listen and scaffold where needed, not removing the challenge. In the midst of students' problem solving, you will ask types of questions and have students engage in the types of interaction that we've been studying. I'm asking that you take students in a small group of 3 to 5 students, that they work on a challenging problem. Like I said, that you interact with them, and that in appropriate places you talk about the challenge, what you're doing and why. For better understanding, see the MAP2-3, which goes into more detail. I'm looking forward to seeing your interaction with students in the classroom. All right, our coming attractions for our next session together will be Mathematical Practice 3, Constructing Viable Arguments and Critiquing the Reasoning of Others. So to determine your prior knowledge and to connect with the topic, you'll complete the MAP Probe 3-1, which has to do with this particular topic of constructing arguments and critiquing reasoning. And in that particular probe, you will once again interact with the video that you are doing of working with students in small groups. So we have multi-purposes for